Hello everyone, my name is MD Faizul Bari and I'm a PhD student at Purdue University, working with Professor Shershin. It is a great pleasure to present my work on a new algorithm that augments trust using non-idealities from RF circuitry for IoT device authentication. We call it DIRAC, which stands for Dynamic Irregular Clustering. We'll start this talk by describing the challenge in IoT device authentication in detail, setting the ground for why we need this work. We're living in a world of smart and connected devices now. Cisco predicts that by 2025, there will be 75 billion connected or IoT devices. These devices often have limited resources in terms of power, computation, or area. They are often employed in remote places, which make them vulnerable to a wide attack surface. Hence, these devices are the weakest node of the whole network, and they define the security of the large network they're connected to. Security failure of these devices can grant an unauthorized personnel access to the whole system. So security failure of the IoT devices can have a huge impact and lead to a catastrophe. Traditional methods use digital signature or secret key based authentication. One widely used method is symmetric and asymmetric key based cryptography, where a private or public private keys are used to encrypt a message. Another approach is two-factor or multi-factor authentication, briefly known as MFM, where a secret password is used, followed by a biometric verification or cross-verification using a secure app or verification token. Open authentication is another prevalent verification method. In OAuth, user resources are stored in a resource server. The user accesses his or her resources using a client app, which requests for an access token from an authorization server, which asks the user for permission. If the user grants access, it provides a valid token to the client app, which can then fetch resources for the user. Despite being widely used, digital signature or key-based authentication methods are vulnerable to various attacks. One major example is cross-site request forgery or CSRF. Let me explain how it works. First, our victim Alice logs in the server using valid secret key. The server grants Alice a valid access token. Then an adversary malware sends a forced request. These requests are extremely deceitful and hard to figure out that they are not authentic. Alice forwards this force request, and since it is sent by Alice, who has a valid token, the server executes the force request and malware becomes successful. Another old trick is brute force attack. Here, the attacker uses an automated tool that tries different combination of the secret key. The weaker the password, the higher the probability of brute force attack being successful. Finally, a major issue of multi-factor authentication or OAuth is that they need manual verification, which is often very hard for a large number of devices. So this discussion proves that the digital signature-based authentication methods have some limitation, and so we need a new method that can augment or increase the security of the traditional methods. The key point here is that our goal is to increase the trust level of the existing methods, not to replace them. So this is the outline of our rest of our talk. First, we'll discuss about the motivation of our work. Then we'll talk about some relevant priors. After that, the whole experimental setup is explained, followed by data processing and analysis of it. Then we describe the algorithm in detail, followed by the results section where the performance of the DIRAC algorithm is evaluated. Finally, we discuss one probable attack model and the robustness of DIRAC against it, and conclude our talk with a brief summary. Okay, we take our motivation from human voice communication, where a person is identified based on his or her unique voice pattern. The speaker doesn't have to say a secret password. Rather, the unique voice pattern in the embedded in the spoken words, uh, rather the unique voice pattern embedded in the spoken words are used, and the listener's brain can identify that. Here, Alice is claiming that his or her name is Alice. Bob, who knows Alice's voice pattern, detects that it is in fact Alice. Now, when Mallory claims to be Alice, Bob finds a mismatch in voice pattern and decides that, okay, it's not Alice. Similarly, each radio frequency devices have similar radio frequency devices have unique physical signatures. They're produced due to manufacturing process variation and nonlinearity and manifest themselves as various system-level non-idealities, which are embedded in the transmitted signal. We call these physical signatures as the voice of the radio, which can be used to uniquely identify a device. Let's talk about a few relevant works briefly. Some authors have used a signal transient to fingerprint our devices. The problem is that it requires proper detection of the transient duration and high oversampling ratio. Bob et al. Proposed RF-Puff and to detect a device using RF non-idealities. However, it requires pre-training and not incremental in nature. Some recent works use deep learning-based frameworks with raw data samples. They lack pre-processing and has high inference time. Okay, so now let's move on to our experimental setup. The conceptual block diagram is on the left and the physical setup is on the right. We have used 30 GP devices as transmitters, 31-bit pseudo-random bit sequence is generated in MATLAB and sent to the transmitter. Which transmits this data to a receiver wirelessly for 60 seconds at 2.465 gigahertz. HackRF1 module is connected to the transmitter through SMA cable, which sniffs this data. GNU radio samples the collected data 6 megasample per second and stores them. Okay, the collected data data samples are grouped into a number of frames, each containing 1200 samples. We found that some frames only contain noise as shown in this red frame. So this is not usable and the noise frames are discarded, and from the usable green frames, we calculate carrier frequency offset. Our analysis begins with the plotting of mean and standard deviation of carrier frequency offset from all 30 devices in a 2D mean and standard deviation plot. Each device evolves with time, so they look linear, just like moving point forming a line. One important thing is most of the clusters are non-overlapping as shown on the right inset, but a few clusters are overlapping as shown on the left inset. This is like the situation where two people have similar voice pattern, which is not so common, but happens. Okay, here the blue curves represent each transmitter, the blue curves is 9. Green region represents authorized and red region represents unauthorized cluster. Traditional clustering approaches, these K-means clustering and density-based clustering, they either fail to include all authorized groups like here, or include other regions like these spaces in green, or these spaces, they can pertain to a rogue device. So they should not be included in authorized list. So we want something compact and tightly defined regions. So discrete and irregular clusters, which are tightly defined around the intended domains and grows dynamically to adjust the cluster with new data, is a much better solution for well-defined clusters in this scenario, which is the basis for the proposed DIRAC method. Okay, now let's explain how our method works. The whole verification is a two-step process. First, we do our initialization for ons, and then we do testing. This is like introducing to an unknown audience. When a new transmitter enters the system, it has to introduce itself. This introduction can be done when a transmitter is being verified by the receiver using a key-based authentication method. We do not utilize the message content as we do not need any key for DIRAC. Rather, the physical signature embedded in the transmitted RF signal during that key exchange is extracted and used. Let's say transmitter TI has n data points. These points are divided into a number of blocks or B. The blocks are formed using moving window approach as shown in the bottom here. From each block, we calculate mu sigma points to get n minus b plus 1 number of points. We call them center points or CP. The last block remains as the current block of the transmitter TI. To summarize that, at the end of initialization, each device will have several center points and a current block containing the last block of B data points. Now, suppose a new data points, dn plus 1, comes in and claims that it belongs to transmitter I. To verify it, we form a test block by excluding the first point of current block and including the test point at the end. So then we calculate the mu sigma from this block and we label it as testing point CX. The increase of B minus 1 previously existing data point helps against catastrophic forgetting, which is common for online learning. After getting the test center point CX, we check two conditions. Firstly, if the Euclidean distance between CX and any other existing centers of TI is less than or equal to a threshold value. Secondly, if the Euclidean distance between CX and any of the existing centers of all other transmitters, like these TJ, where J is 2 to 30, is greater than the threshold. If CX fails to satisfy any condition, we reject its claim of pertaining to TI. So in effect, a cluster of TI is formed by combining all the circuits around the center, like here, these black dots are the center points, and we're forming a circle of radius threshold. These circles in combine form clusters for TI. So one important thing here is that the clusters grow dynamically. And the other thing here is that if the initial center point is too low, as you can see here, the clusters are not properly defined and the value point cannot be detected properly. But when the initial center point number is high, the circles overlap closely and they form nice uniform cluster. So that effect of initial data point is directly reflected in our result. So as you see, the increasing the initial data point increases accuracy in both non-overlapping and overlapping cases. However, we have one interesting phenomena here. When the initial data point is low, the block size B is significant, and its effect can be seen here because we have n minus B plus 1 number of center points. But when n is large enough, it can offset slight change in B. So all these curves merges. The other interesting phenomena that we see for overlapping transmitter is that sensitivity saturation. So what's happening here is that when a point is overlapping, that is, it remains to both clusters, it fails to satisfy the second condition because it's in neighborhood of another cluster always. So there is always some count of false negative which cannot be avoided, and that limits the maximum sensitivity to a certain number. For our case, which is 98%. Another important thing is we're reporting our performance in terms of sensitivity, not accuracy here, because we have class imbalance with one target cluster as true class and all other 29 clusters as false class. This gives high true negative count, so we use sensitivity which doesn't use true negative and is a ratio of true positive over true positive and false negative combined. The threshold value determines the radius of the circle around the center, so the width of the clusters, if it's too and the width of the clusters, yeah. So if it's too high, the neighboring cluster starts to overlap and the accuracy starts to drop, which can be seen here. So after the threshold value of 1 kilohertz, the sensitivity starts to drop because after this, the clusters starts overlapping here. Okay, next let's talk about the incremental learning feature. So as we have said earlier, our clusters grow dynamically. So their accuracy improves more and more with more testing data. So it learns incrementally as it is shown here. So as the number of test data points increases, the sensitivity also increases. So now we discuss about one probable attack model. Here the attacker captures the transmitter signal, modifies the data in digital domain, and converts the data back in RF domain, so that this RF signal here contains the same non-idealities as it was in the original signal, so that the receiver gets spooked because the receiver is basically checking the RF non-idealities. But doing this requires extremely high precision ADC and DAC, also very high bandwidth filters, and also very fast circuitry, so that the delay is significantly high. So due to this, the limitation, bandwidth limitation and resolution limitation, this attack is practically impossible. So our method, or DIRAC algorithm, is almost more or less robust against replay attack. Okay, so now let's finish our talk with the brief summary of what we have done. So we have shown that physical signatures from RF circuit and systems can be used to augment trust during digital signature-based device authentication. A new dynamic irregular clustering algorithm is proposed, which requires only 0.2 millisecond of test data, that is, which is like one frame. Test data to provide more than 95% sensitivity and reaches around 100% accuracy or sensitivity at optimum point. The design space has been explored of the proposed algorithm. One probable attack model, that is replay attack, and robustness of DIRAC against it have been discussed. The proposed method learns incrementally as more and more data are available. DIRAC can add an additional security stage to the existing key-based authentication method without putting any significant burden. So it doesn't need to require any additional block in the transmitter side. So it can render the overall device authentication system more secure. Thank you for listening to our talk.